So let me introduce participant, Dr. Mehdi Zareb, a research scientist at Capgemini Engineering in Blagnac, France, has over 13 years of experience in research and development. He holds a doctorate in automation from Université d'Ivory, University Paris, Sekeli. His expertise includes ecological transportation technology, resilient control systems, and Internet of Things applications. Dr. Zareb has contributed to numerous industrial projects, including advanced control systems for drones that apply ADRC and PEMFC based hybrid propulsion systems to eVols. He developed IoT solutions for smart homes, air quality monitoring, and UAV applications in smart cities like traffic management, population tracking, etc. Additionally, he has managed innovative studies in robotics based on artificial intelligence diagnostics and automation. Experienced in MATLAB, Python, Simulink, he integrates control systems for environmental and urban applications. Dr. Zareb is fluent in French and English and actively contribute to scientific community through publication on platforms like ResearchGates, Scopus. Passionate to sustainability, he promotes the advancement of mobility and smart city technologies. So we welcome Dr. Zareb. Uh, Sir, you can start with your talk. Sir, your microphone is mute, I think.
Hi.
Yes, yes.
Yes, yes.
Yeah. I'm sorry.
Okay.
It was muted. Yeah.
Okay.
You see my presentation? Is everything is okay?
Yes.
Okay.
Yes.
Okay. Thanks. I said that I'm very happy to be again with you. Thank you. Thanks to the professor and the committee of organization to invite me.
Okay.
It's a pleasure to be here. Also, I'm very happy to present this subject. I think it's very important. It's a very important subject in advanced technology, AI, and the automation and diagnostics. I spent 4 years teaching this module for the master's students for 5 years, and also for my subject of research, I used the AI in automation. And in fact, I think it's very important to address this kind of subjects in details. So let's start with presenting the plan of this presentation. First of all, we will introduce the context of the subject, the importance of the diagnostics, and we will see some two examples of catastrophe due to the to faults. We will also make some present some definition and concepts. It's very important. There is a lot of definitions in this in the diagnostics, and I try to just summarize two definitions, and I let a reference for the audience to see more definition, because it's very important to define and to understand each concept. Then we will, in the fourth point, we will get to the point of this presentation is why we prefer, and it's preferred to use artificial intelligence. We'll see also some tables about comparison between the model-based and the AI-based diagnostic systems. We'll see also the different types and methods of the artificial intelligence. The seventh point, I selected a paper that's resume all the AI fault diagnostics methods using in electric machines. Then we will get to the fault diagnostic techniques for nuclear power plants with another example, and at the end, conclusion. Advances in technology have increased the level of automation in industry, but they have made systems increasingly complex, placing higher demands on system safety and reliability. One way to improve the system safety and reliability is to improve the quality, the reliability, and the robustness of the system compound, but this still cannot eliminate the occurrence of faults. In the picture we see here, one of the biggest disaster of Chernobyl, for a nuclear plant. This catastrophe, the main cause of this catastrophe, it's due to the fault in the AR2 system. It's a control system. And everyone know the impact of this catastrophe since 1986. Another example caused by operational fault is the Piper Alpha disaster in 1988 in the North Sea. This is caused because of the operational faults and the safety procedure violation. Here we can understand the importance of diagnostic system. As an engineer, automation engineer or researcher, we give a lot of importance to the design of controllers, stability, all the performance of the control system. But the importance of the diagnostic systems is much better than the control system. So the main goal of this presentation is to understand the limits of classic diagnostics, the role of AI in both automation and especially in this presentation about the diagnostics, and we will see which methods to choose a diagnostic AI diagnostic strategy based on the two examples that we will introduce. So the motivation of this designing diagnostic systems is that the industrial systems are complex, and now they became more and more complex. Here we speak about the industrial system, but the rules are we can extend the rules for all the system, electric vehicles, every kind of system. Second thing is the fault appear early, and the alarms appear late. And the key facts is that the maintenance costs up to 40% of life cycle. So this is the first one. Is the first motivation? It's about security, and the second one is about cost. And we need to know that the design of the diagnostic system is very expensive than the control system. The use of the diagnostic system. Where we use the diagnostic system? We use the diagnostic system in the aircraft system, emission control in vehicle, nuclear plants, chemical plants, gas turbine, and industrial robots. So the the goal of designing a diagnostic system, first of all, as we can see, this is about the safety. The second one is environment protection, the machine protection, availability and repairability, and flexible maintenance. This is the six main goals for the design of the diagnostic systems. Now we get to the basic definition and concepts. The first aspect is word is the faults, and we can define the fault as unpermitted but deviation of at least one characteristic properly or variable of the system from acceptable usual or standard nominal behavior. For example, we take an example. We can for a heat system. So the temperature of this system, it's usually in a nominal value. It's about, let's say, an example, 100 degrees. And when we observe that this temperature is increased without any reason, so we can conclude that there is a fault about this system. So this is all about is a deviation of the characteristics of a variable of the system. The second term is the fault diagnosis. From the definition of this term, two common views exist in the literature. The first one, they define these terms that is include fault detection, isolation. That means in the system we isolate. That means we define the faults, and identification. And the second view includes only fault isolation and identification. So we can find these two of, but the most one is the most definition. It's the first one. When he said that we do a fault diagnosis, that means it includes fault detection, isolation, and identification. And for more details, we can see the references highlighted in this slide. So, in the automation or in this new philosophy, we can find two parallel designs. The first one is the design of the control system. This one, I think, most of the students and the researchers know this about this. It starts with the specific objective control objectives, and then we model the process, design the controller, we verify the stability and the performance, and then after that, if the performance is acceptable for us, so we implement the controller. If not, we restart from the design of the controller, and the same. We do the same in the when we want to design a diagnostic system. First of all, we need to specify the force to detect, and we need data acquisition, and then develops diagnostics models, and then we implement the diagnostics models to make decision. And sometimes we make decision. We speak about the active diagnostic or passive diagnostic is just to know the if there is a fault or not. So a physical system is contained of three main compounds: the sensors, which is the inputs, the controller, and the actuator. And the faults can appear on the three of these compounds. First, it appears on the sensors or the actuators, or sometimes it's not usually it appears on the controllers. And the diagnostics system is often added after the control. That means when everything is okay with the control and all the performance is good, we start to made a diagnostics system in parallel with this control system, and it gives these structures. So this is a general structure of diagnosis application. We can see the plan is fully automated with the controller, and a diagnostic system is um, uh, connected to the control of the plant, and using observations here, I will speak about and detail this the elements of the diagnostic system. We can isolate and then made what we know as a diagnosis statements. We take an example, a simple example, a simple way of understanding the diagnostics. This is the electrical circuits, battery with a switch and a lamp. We can simple the diagnosis system of this circuit as a lookup table. In the first diagnosis statement in this table, there are two diagnosis indication singles false. S is stack open and L broken, and the two diagnoses indicating a multiple false, S stack open and L broken, and S is stack close and L broken. Let's take an example. Let's take the case when the switch position is open and there is no light. So the diagnostic statement here, it means that even there is no false, or there is a stack of the switch, or there is a or the light is broken. This is the kind of reasoning. So all this diagnostic system can in principle be presented as a table. It's a simple way. However, then the numbers of possible faults increase. The table quickly becomes very large. So for the future problem, this kind of tables cannot handle. So we need more way to design the diagnostic system. Here we speak about the solution is the model of the system. I mean, we use a knowledge. The first knowledge about the system is the models. As we know, in a classic control, we can use the state space, and we can use a very important element in the design of the diagnostic system is the observer. Any kind of observer, Kalman filter, Lemberger. So we know in the control, in the classical control, we use the observer as a state estimation. So we use this information for the control, but also in the case of the diagnostic system, we use this observer to generate what we mean residual generation. That means this residual, based on this residual, we can detect and isolate the faults. So the residual is the inputs of the diagnostics system. It's an error between the measured and the estimated outputs of the system. So if this error is thresholds, that means that there is a fault. The advantages of the using models, is interpretable. That means that we can easy understand the each fault and the causes of the faults. But this the model-based diagnostics are limited. First one is it's very sensitive to the noise, and then it's sensitive to the parameters drift. This is the two main limits. And after that, we will see in details the comparison between the AI-based diagnostics approach and the model-based. So now we get to the point of this presentation. Why artificial intelligence is useful for the design of diagnostic system. First one, the idea is learn system behavior from data. This is the first one. And then no explicit physical equation required. And AI techniques sees patterns, and humans miss patterns. And then the key question here is, can data replace models? So at the end of the we will see the comparison between the AI models, AI made based techniques and the model based techniques. At the end of the comparison, we will respond to these questions. So now, actually, there is two main axes for the design of the diagnostics systems. The first one, and it was the and is still also used the model-based diagnostic system. It's based on the model, and it's made a compare predictive and measured data. It generates and analyzes the thresholds of residual analysis, and then it allows to detect the faults. That means the deviation from the models. But in another way, using AI-based diagnostic system, we base this this diagnostic system is based mainly in the training data and AI models to recognize the patterns. Here there is two kind of patterns, normal or false, and then the anomaly or the false are detected. And this is the two main approach for the diagnostic system. Here I prepared some of the table that resume and summarize the model-based diagnostics and the artificial intelligence-based diagnostic systems based on criterions. First of all, as we have seen the definition, the first one, the model-based use the mathematicals or the physical models to detect the derivations, and the artificial use data-driven from algorithm, machine learning, deep learning, physiologic. We will see all the different type of the algorithm to learn pattern from historical data and detect defaults. The principle of the model-based, it compares the measured system outputs with those predicted by unknown models. For the artificial, it learns normal and faulty patterns automatically from data without need an exact physical model. The knowledge requirement for the model-based requires a deep understanding of the system physics and the equations and the dynamics. But in the case of the artificial intelligence, it requires large data sets from system operation, normal and faulty conditions. In the two, we need the information for the two patterns. If we get the high accuracy in the mathematical model is precise, and environmental conditions are stable. High accuracy in enough labeled data and robust AI algorithms are available. For the adaptability, so for the model base is limited, it must be redesigned if the system structure change. For example, if we add a sensor, if we made some change. Also, there is a limitation about the parameter variation due to the parameter variation. But this is very high. This criterion is very high in the case of the artificial intelligence, because um, uh, most of the AI algorithms have the self-learning and can adjust to new patterns using uh, retraining. That means that we don't need to change all the structure of the diagnostic system. It's just we made another we retrain for example, if we have a neural network, we retrain our neural network to learn about the new patterns. The criterion complexity, it's very complex to design a diagnostic system for non-linear system, time varying and uncertain dynamics. It's very there is a difficult of the form to model this kind of nonlinearity. We need to. It's very important to know that the majority of the approach model-based diagnoses are designed for linear systems. But in the case of the artificial intelligence, this nonlinearity are handled with efficiency. This means this is the I think this is the most important criterion when we compare the artificial based diagnostic system and the model based. Getting to the computation time, usually faster in real time once model is built. Simple residual and calculation. This is the advantages of using model-based diagnosis. But in another case, in the AI model-based, it requires significant computational power, especially when we are using deep learning models. So, example of techniques. Example of techniques, there is in the we know for the model-based diagnosis, we know the Kalman filters is largely used. The all other type of observers, parity equation, and residual analysis. This is the main techniques in the used in the model-based diagnosis systems. In the other side of the AI techniques, we found the most and the large one is the neural networks. SVM, support vector machine. Physiologic form I have used implement with the students in master project physiologics to detect a fault in an industrial plan, and it's very simple to implement. Physiologic, it doesn't need a huge data set to be implemented. I'm very fan of the physiologics. This is why I deep learning, also genetic algorithm. I also recommend this kind of algorithm to example of application: nuclear reactor control system, aerospace engineer monitoring. For the AI intelligent-based diagnostic system, we can find an application in a smart factoring, predictive maintenance, and rotating machinery, and a lot of application in robotics. So the main limitation, to resume, for the model-based diagnostic system, it's not suitable for a highly complex or partially unknown system. For the AI based diagnostic system, it requires large, high-quality data set and a careful model validation. This is the main limits of the AI techniques. So this is a spinal chart that summarize the six criterion. There is the model-based and the AI-based. The model-based is in orange, and the AI-based is in dark orange. So we can see that the AI-based diagnostic system is very good for the most of the criterion, but in the accuracy and but on the other hand, it's very complicated. It requires data. It's not the model base is very simple, but it's limited because if there is some change in the plan or the system is complicated, or the system is there's some behavior, nonlinear behavior that we can't model, though. So the model base is not recommended. Here it is a table that summarizes the strengths and limitation of each method, each approach. Sorry. You can see that the AI based it's larger, have larger strength in the than the model based. We can see the main one is that it's the adaptability of the AI based diagnostics approaches. This is the main one. There is a lot of systems that are highly complicated. There is a lot of change sometimes in the industrial plants. So this adaptability, this criterion is very important because the AI based are highly flexible, adapted to new data pattern. This is the most important strength in my opinion. So to resume, so if we have a system with a well-known physics, directly the model-based diagnosis is the best choice. If we have a complex of or data-rich industrial system, and the system is frequently changed, we need so the AI-based diagnosis is the best choice for the design. But if we need interpretability and traceability, that means we need to understand the faults, how it's made. So the model base is the best choice. So we can see here, if we want to answer to the questions, there is no better approach. So it depends of the aspects. So because of the main the subject of this presentation is artificial intelligence, we will go for the analyze of the different artificial intelligence based diagnostics methods. So we can divide these methods in the first group is the single algorithms AI-based diagnostic system. We found the famous artificial neural networks, the SVM, principal compound analysis, decision tree, and clustering, key means, and for example, I take just one because I have a lot of is no time, I think. There is for example, for artificial neural networks, it is very easy to implement. The principle of these methods is that it's mimic biological neurons learn nonlinearity intershift from data used for pattern recognition and fault classification. The advantages of these methods, it's a high accurate, it's very adaptable to the nonlinear modeling. And the limitation of these methods, it requires large data sets and less interpretable. And this is the limits. The second group, and now it's the main research axis, is using hybrid AI diagnostic methods. That means each method, as we have seen, single methods has limitation and advantages. And going forward for a hybrid algorithm, we can combine the advantages of each single methods, and then having a very powerful algorithm. We take an example here, the hybridation between physiologic and neural network. This combination, it combines the fuzzy reasoning with neural learning for uncertainties handling. For example, reactor control and anomaly detection. And there is also a lot of way to combine different single methods. For example, a larger one that combining the SVM with the neural networks. It's the purpose is to integrate SVM's boundaries detections with neural network learning ability. For example, it's this kind of hybridation. It's application in the system level fault protection. Now we will see the first example of using the AI for fault diagnosis in electrical machine. I have found this article very interesting. This article analyzes the several AI techniques that detects and classify faults in rotating electrical machines. The goal is to improve reliability and safety and maintenance efficiency for this electrical machine. It's known that the electrical machine consume 40% of the electrical power. The electric machine consume over 40% of the global electricity of all kind of rotating electrical machine. An expected failure of this kind of machine cause high economical and safety risks. So the classical diagnostic methods struggle with noise, as we have seen. I mean here with classical diagnostic methods based on a model, struggle with noise, multiple defaults, and the changing operating condition. So a good way to detect faults is to design diagnostic system based on AI approach. So the main fault type for electrical machine, the first there is a lot of several categories. The first one it's about the stator faults, where it insulation degradation, enter-turn short circuit, fast to fast and fast to ground faults. This is the main fault in the stator. For the rotor faults, we can find a broken rotor bar, a ring failure, static and dynamic problem. For the bearing faults, we can find an inner race defect, outer race defect, ruling element fault, cage defects. There is a lot and other failures about the shaft, similarly air gap, irregulating, cooling system failure for some of the high power machine. For the data and sensing, multi-sensor monitoring using currents, voltage, vibration, temperature, and acoustic emission. Sometimes we found the faults appear in the sensor of this machine, a different sensor. Also about the signal processing, about the frequency, the filters, all these signal processing elements. That's where the faults can appear. So in this paper, the paper highlighted multi-sensor monitoring. For example, for the current sensor, vibration sensor, acoustic emission. Also, the authors analyze the different time domain features, time frequency methods, all the comparative analysis of for the paper for each methods. He compared each method, compared the accuracy, the interpretability, the data requirements, the computational chaos, the industrial applicability. So all these criteria were the main compare metrics for the paper, and the conclusion is that there is no single method fits all cases. Model choice depends on data availability and deployment constraints. That's very important. If we have no available data set, all the AI methods cannot work. Here in this table, I have summarized the different AI approach studied in this paper. We can list the supervised learning, unsupervised learning, deep learning, hybrid, and ensemble methods. For example, for the supervising learning, taking the main methods was the SVM, decision tree, random, and neural network. The key points is this supervising learning have a high accuracy with labeled data, and it requires expert feature engineering. I will go directly to the hybrid and ensemble methods. The main methods is the neurophysics systems. as I said, this hybridation improve robustness and generalization. Here there is an example of a diagnostics framework for PMSM, permanent magnet synchronous motors, using multi-sensor signal fusion and image features extraction. This work was presented in the reference number 1, and the idea here can see here the experiment signal experiment platforms. The idea here there is several multi-sensor signals and an image generations, and this and all this information are used to improve the training stability and the what we said the depth of the training when using several source of information. The goal of this framework using multi-sensor um, multi-sensor information to first of all to train the graph neural networks, and then having a robust diagnostic system that can detect the faults. So the challenges identified by the author in this study is that the lack of labeled industrial data, and this is very important, because if we don't have a labeled industrial data, we can't train the different neural network, for example. Poor generalized across machines, black box behavior of deep models. This is very challenging, because let's say if there is a problem with detection some of the false, and then we can't know what is the real issue. So this is very important. And the future directions of according to the authors is explainable AI to overcome the problem of the black boxes behavior. The second direction is the self-supervised learning, transfer learning, edge and cloud hybrid employment. The second example is the applying this article is study the different AI artificial techniques for a nuclear power plant. So the paper study the use of AI-based hybrid methods, and the conclusion here, the key insight is that it concludes that the AI-based hybrid methods, especially neural network hybrids, lead to fail in nuclear and industrial fault diagnosis due to their superior adaptability and accuracy, while interpretability remain a challenge. So this is the black box challenge. So the main structure of the nuclear plan can be summarized as presented by this picture. It's a simple nuclear reactor with a cold water system. So the paper have summarized the or regroup the all the intelligence artificial intelligence methods in two groups. The first one is knowledge-driven fault diagnostics and data-driven fault diagnostics approaches. So there is a lot of methods, and in this study, they have regrouped or summarized the all these methods into the first one, the knowledge-driven fault diagnostics. It relies on expert knowledge, logic, and causal reasoning to detect and diagnose faults. It uses knowledge-based expert rules, causal graph, and interface machine for reasoning. The core principle of this approach the use of a human expert experience and system causal logic to infer fault from symptom. So this is the first group. We can see the famous methods. We can classify these methods, the fuzzy logic reasoning. The second approach is data-driven fault diagnostic. It uses measured data and machine learning algorithm to automatically learn fault patterns without relying on physical models or human knowledge. It combines a large data set with a training inference models. The core principle of this method is learns a relationship between inputs and faults directly from data. So if we compare these two, this table compare these two principal approaches. Let's take just one aspect, the typical techniques, or the let's say two. The first one, for the knowledge-driven methods, we use the if-then expect system as the physiologics. But in the data-driven methods, we can find, for example, the neural network or the VSM methods. For the data requirements, the knowledge-driven methods requires limited operational data released on expert knowledge. This characteristics made the knowledge-driven methods simple to implement. See, the data-driven required large, high-quality data sets, and this is the main important comparison. To resume all this comparison between the knowledge-driven fault diagnostic and data-driven fault diagnostic, the advantages of the knowledge-driven fault diagnostics is explainable and logical and strong in noise and uncertainties. And the data-driven fault diagnostics, the advantages is that it's very robust to sensor to noise for the sensors, and it's very the data-driven faults. It's very powerful in terms of adaptability. And as a conclusion of this study, the trend is to integrating both approach to improve the diagnostics performance. And this is the conclusion for this paper. Is that they said that the knowledge-driven methods represent the first generation for the AI methods, while data-driven methods represent second generation. The combination between knowledge interpretability and data adaptability is the future direction for intelligent fault diagnostics, especially in safety critical fields like nuclear power plant. So this is the conclusion. So to respond to the first question, so the a good fault diagnostic system based on the AI methods. The best one is that the one who combine knowledge, interpretability, and data adaptability. This is the conclusion. Sorry. And for as a conclusion of this this presentation, so the model-based systems are best for well understood physical-driven process, but the AI-based systems excel in complex data rich and dynamic industrial environment, offering flexibility and predictive capability. At the end, the final question: if your project, where should intelligence be? In the models, in the data, or both? And thank you for your attention.
Uh, Thank you very much, Dr. Zareb. Participants, if you have any question, you may ask in the chat box. I'll print it out for this. Yes, participants, anyone? Okay, sir. I don't think that there is anyone who's having any question. So, Dr. Zareb, we thank you from our a big thank you from our institute and all the participants. It was a very interesting and detailed session that you have given insight to the applications of AI/ML to IoTs and other applications. So thank you very much, sir. I look forward
Thank you.
to see you again.
Thank you, sir.